Hi everybody, this is part 2 of the relative motion video. I'd like to do a couple of problems here. Let's take an airplane problem. Okay? And remember, in review, I want to be able to use the relative velocity formula here, where you have, well, I'll put that later. Let's say that we have a pilot who wants to fly from A to B, point A to point B, straight east. If I put a compass rose up here, let's see, that up would be north, down would be south, to the right would be east, and to the left would be west. Okay, so there's my compass rose here. So the pilot wants to fly from A to B, which is directly east. B is directly east of A. Okay, but there's a wind. Okay, and the wind is directly pointing south. It's going from north to south at 100 miles per hour. It's a big, strong wind here. So this would be the velocity of the air with respect to the ground. Negative 100 miles per hour, pointing down that way, right? And we also have the pilot sets the speedometer at 600 miles per hour, and the speedometer reading is relative to the air. So the velocity of the plane with respect to the air, it's going to the right, we can call it positive, would be a plus 600 miles per hour. Okay, so we have velocity of the plane with respect to the air, we have the velocity of the air with respect to the ground. We should be able to get the velocity, let's say we want to find the velocity of the plane relative to the ground. Well, that shouldn't be too hard. Using our little relative motion idea, we have the velocity of the plane relative to the ground is equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground. Okay, and using our dimensional analysis approach, we can see that this term here is the same as this term there, so they will cancel out in using our little memory helper idea. And that just leaves us with VPG, which is what we have on the other side too. So this should work out okay. Let's draw our little vector diagram. Okay, so this right here would be the velocity. Let's say this is the vector for velocity, the velocity of the plane relative to the air. That's plus 600 miles per hour. I'm not even going to put the units in this time. And then I'll touch the tail of the velocity of the air with respect to the ground. That'd be velocity of air with respect to the ground is negative 100 miles per hour. Okay, that one goes there. This one goes here. And our resultant would be from where we start to where we finish. It would be this arrow here. That would be the resultant. And that would be VPG, which is what we're looking for. Okay, well, and this is a right angle. This is just your typical vector addition problem that we've done in the past now. Okay, it's no problem. If we want to find out this, the magnitude of the velocity of the plane with respect to the ground, that would just be equal to we can use the Pythagorean theorem. That'd be 600 squared plus a negative 100 squared, and we get 608 miles per hour for the magnitude of the velocity of the plane with respect to the ground. Now, since it's with respect to the ground, that means that that's not the speedometer speed, that's speed relative to the ground. That's the speed that somebody on the ground would measure the plane as going at. Okay? How about the angle? Same approach as we've used in the past. We can just take that vector triangle and use the inverse tan of the opposite over the adjacent side. So that'd be 100 over 600. You can put a negative in there if you want, but all we care about is the reference angle. And if you do the math, that comes up to be 9.46 degrees. So, in summary then, the velocity of the plane with respect to the ground, I can just write that, velocity of the plane with respect to the ground, would be 608 miles per hour a 9.46 degree angle. Now, where would the person end up? Well, it depends how long of time it takes, how many hours, but you can see that if that person pointed their plane, I'll just draw how the person's pointing their plane in this case. There's the axis of the plane, here's the wing, and then here's the tail section. Then after another period of time, the plane would be here. Notice that the pilot is pointing the plane directly east at every instant, but the wind is pushing the plane diagonally, so it'll end up at X marks the spot there. Okay, so the pilot points the nose east, directly straight east. However, the pilot gets shifted off the path and ends up here at this point instead of at B. Okay? Now, a smarter pilot might be able to avoid getting knocked off the path like that by aiming upwind instead. So let's see how that would work. So let's take a smarter pilot, aims upwind. So we still have our negative 100 mile per hour, should say, velocity of the air with respect to the ground, and we still have the speedometer speed of 600 miles per hour, but that's the speed of the pilot, or the plane I should say, with respect to the air, because the speedometer, airplane speedometers measure speed in compared to the airspeed. Okay, they use what's called a pitot tube, and I can explain that in class later to you. Okay, anyway, the velocity of the plane with respect to the air is plus 600 miles per hour. Okay, but the pilot wants to go from point A to point B without being shifted off track. So the pilot's going to have to aim upwind. So instead of aiming the plane directly toward point B, the pilot's going to point the plane, the axis of the plane, upwind. Here's the wings and there's the tail. So at a certain point in time, the plane will be here, but notice that it's still pointing upwind the whole time by a certain amount. Eventually the plane's going to get over to point B, but notice that the plane is angled towards some other location. So the plane's going to end up here. Okay, so how do we do that? Well, let's draw another vector triangle here. This time we have our negative 100 here pointing from A to B like that. This would be the velocity of the air with respect to the ground. And then we have our 600 mile per hour velocity of the plane with respect to the air here. And then this distance here, or actually this right here, would be the resultant in this case. So here now we have the resultant in red. Okay? And the angle would be this angle here. So let's use our relative motion formula again, and let's see how that would work. Okay, we have the velocity. We want to find the velocity of the plane with respect to the ground again. So that's the velocity of the plane with respect to the ground is equal to, now we see that these two are tailed ahead, so that means that they would add up together to form this resultant here. So the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground. We see that these two terms here are the same, A and A, so they can cancel out like that. And that just leaves us with velocity of the plane with respect to the ground. So we know that that will work based on our tailed ahead vector triangle. Okay, These are vectors now, and they both have vertical and horizontal components. So we ought to split that up and just say, okay, well, let's do that. Okay, so we have the velocity in the of the air with respect to the ground. Does it have any x component? No, it's all vertical, so there's no x component. How about the y component of the velocity? Well, that would be negative 100, wouldn't it? How about splitting up the velocity of the plane with respect to the air? Okay, well, I can just draw, we have a 600 mile per hour hypotenuse. We don't know what the angle is, but we do know, and we want to find out what the vertical component is here. Okay, that's Vy of the plane with respect to the air. Okay, so how do we find that? Well, that would just be 600, let me get that up a little bit here, times the sine of that angle. So this is equal to 600 times the sine of whatever this angle is right here. Okay? Well, what does that have to be equal and opposite to? That has to be equal and opposite to 100 miles per hour, right? In other words, the pilot's vertical component of his or her velocity has to be pointing upward, which cancels out that downward velocity of the wind pushing on the plane. So we can say that the vertical component here, the velocity, is equal to 100 miles per hour. And knowing that, then we can rearrange the sine theta then would be equal to 100 over 600, and therefore the angle would be equal to the inverse sine of 100 over 600, which gives us 9.59 degrees for this angle right here. Oops, sorry, let me move down. So this angle right up here is 9.59 degrees. That's how much the pilot has to angle the plane to compensate for the wind. If we wanted to find out the magnitude of this right here, we could still just continue on this process. I kind of drifted off a little bit from that process, but we could continue with this process here, and we could break this component up into two parts. We know this is 600 sine theta, which is equal to 100, so the vertical component is 100, and this horizontal component we can find out. Okay, so that's a positive 100 here, and then this is what? 600 times a cosine of 9.59 degrees. So if I go ahead and solve for that, put it in degree mode, we get 592 approximately. 592 miles per hour. So this is the x component of the velocity of the plane with respect to the air. The x component of velocity of the air with respect to ground is 0. We add the two up, it comes out to be 592. These two added up add to be 0. So, to make a long story short, probably overcomplicated the problem for you, but the velocity of the plane with respect to the ground, that's horizontal, that would just be this answer right here. 592 miles per hour. The only reason we needed this here was just to use dimensional analysis along with our tail-to-head vector triangle to kind of reassure ourselves that we're on the right track. We could have gotten by without this to do the problem. Well, anyway, that's part 2. Thank you very much.